Have you ever, read a fantasy novel or seen a movie where someone has this tiny bag, but they pull out something enormous like Hermione Granger's bag in Harry Potter? It looks small, but, there's practically a whole room inside.
Yeah, that idea, the magic of fitting this huge space into something small and stable, it sounds like pure fiction.
Exactly. But it's not anymore. That's
Huh.
pretty much the core idea behind the 2025 Nobel Prize in Chemistry.
It really is. The Nobel Committee even used that exact Hermione analogy. We're doing a deep dive today into these things called metal organic frameworks, or MOFs.
MOFs, right. And they're this completely new class of materials, engineered materials.
An entirely new class, yeah. And the promise here is, well, it's huge. They could genuinely change how we tackle massive problems, from, say, cleaning up CO2 emissions to even getting water in deserts.
Okay, so let's get into that. Our mission today is to unpack the research, the decades of work, really, by the three scientists who just won the Nobel for this. The Royal Swedish Academy of Sciences announced them on October 8th, 2025.
That's right. We're talking about Suma Kitagawa from Kyoto University in Japan,
Okay,
Richard Robson from the University of Melbourne in Australia,
got it.
and Omar M. Yagi. He's at the University of California, Berkeley in the U.S. These three are basically the architects of this new molecular world.
Architects of the molecular world. I like that. So their genius gave us MOFs. Can you give us the quick definition again? What are they?
Okay, concisely. They're crystalline materials. Think like salt or sugar crystals, but engineered. They're built from tiny molecular building blocks
Okay.
and designed really precisely at the atomic level to form these structures that are just incredibly porous, full of tiny, tiny holes.
Right. Pores.
Yeah.
And why should you listening care about microscopic holes?
Well, because these tiny pores add up to something enormous.
Mm.
These materials, they have this extraordinary potential to help solve some really big global challenges. We're talking climate change, water scarcity, even better ways to deliver medicine.
Okay, let's unpack the structure first. You said designed. That feels key. Usually in chemistry, you mix stuff and see what happens, right? A bit of trial and error.
That's often been the case, yeah.
Yeah.
But MOFs represent a shift. It's about rational design. It's much more like architecture or engineering, but at the molecular scale. You draw up a blueprint for the atoms.
A blueprint for atoms. So less happy accidents, more deliberate construction.
Exactly. Forget trial and error. This is systematic. Think of building a 3D structure, like a climbing frame or a net, but using molecules as your parts.
Okay, so what are the parts? If it's like molecular Lego, what are the bricks?
Good analogy. There are basically two main components. You've got your cornerstones, these are metal ions, or sometimes small clusters of metal ions. Technically, we call them secondary building units, or SBUs.
SBUs, the cornerstones. Are
They act as the joints or the hubs in the structure. And then connecting these metal hubs, you have the linkers.
the linkers. And these are the struts, the beams holding it all apart.
Exactly. They're usually longish organic molecules.
Hmm.
And here's the clever bit. By choosing different metal SBUs, different shapes, different sizes, and different organic linkers, different lengths, different rigidities,
You can basically pre-program the final structure.
you got it. You pre-program the size and the shape of the empty spaces inside the rooms or cavities at the molecular level.
Yeah.
And that design dictates exactly which molecules can fit inside, which ones get trapped, and how they get released.
Okay, that control sounds powerful. But let's get to the wow factor you mentioned, the porosity. The sheer amount of empty space. Remind me of that number? It's kind of hard to believe.
It really is mind-boggling. The record surface area for some MOFs,
Yeah.
it gets over 7,000 square meters in a single gram of material.
7,000 square meters per gram.
Per gram. To put that in perspective, imagine taking a whole American football field, sidelines and end zones included,
Okay.
and somehow compressing all of that surface area down into something the size of a single sugar cube.
That's just nuts.
Yeah.
A football field in a sugar cube. No wonder they're so good at grabbing things.
Precisely. No other material we know comes close to that kind of internal capacity. And this ability to design these nets, it actually led to a whole new branch of chemistry,
Oh, yeah. What's it called?
reticular chemistry. It comes from the Latin word reticulum, which means small net. It perfectly describes these structures,
Reticular chemistry. Okay.
but it's more than just a name. It's about the philosophy of predictability. It gives chemists reliable design principles, like a rule book, for building these extended porous structures rationally, instead of just hoping for the best. That was a huge leap.
So it's about moving from discovery to actual design. Now, this didn't happen overnight. It took these three laureates tackling different parts of the problem, right?
Absolutely. It was a progression, with each one building on and sometimes solving the limitations of earlier work. It's a great story of scientific progress.
Let's start at the beginning then. Richard Robson in Australia. His work was foundational back in the 80s.
Way back, yeah, the late 80s, early 90s. And his inspiration, believe it or not, came partly from these old-school wooden models of crystals he used to build for teaching chemistry lectures back in the 70s.
Seriously, wooden block.
Yeah, playing with those physical shapes apparently gave him this key insight. You could use the geometry of molecules, their inherent shapes, to kind of pre-program how they'd connect.
Like designing puzzle pieces that could only fit together in one specific way to build a bigger structure.
That's a perfect way to think about it. It sounds almost obvious now, maybe. But back then, when his key paper came out in the Journal of the American Chemical Society in 1990, a lot of chemists were really skeptical.
Why? What was the pushback?
The common wisdom was that trying to assemble complex structures like this from solution would just result in a mess, a random jumble. They literally called it tangled birds' nests. Just useless gunk.
Tangled birds' nests. Okay.
But Robson proved them wrong. He successfully created the first deliberately designed 3D coordination polymer, that's the technical term, with a specific, predictable, ordered structure, a diamondoid structure based on the diamond lattice. He showed it was possible to design these things.
So Robson laid the blueprint. He showed you could build it. But was it useful yet? What was the next big hurdle?
Well, just because you can build a framework doesn't mean it does anything interesting or does it well. That's where Susumu Kitagawa in Japan came in. His major contribution wasn't just about the static structure, but about its behavior.
Behavior. How can a crystal structure behave?
By being flexible. Think about traditional porous materials like zeolites. They've been used in industry for ages in catalysts and filters. They're very rigid, like porous rocks.
Okay, rigid sounds good, right? Stable. Why do you need flexibility? Wouldn't that make it weaker?
That's the counterintuitive part, and Kitagawa's great insight. He showed that MOFs could be dynamic, flexible. He called them soft, porous crystals. This wasn't weakness, it was a feature. He introduced the concept of breathing.
Breathing. The MOF breathes.
Kind of. The framework can actually change its shape subtly.
Yeah.
It might expand slightly when it absorbs gas molecules like methane or CO2, especially under pressure, and then contract again when the gas is removed. A bit like how our lungs expand and contract.
Ah, I see. So a rigid box has a fixed volume, but a breathing box can sort of adjust to hold more or release easier.
Exactly. This dynamic behavior turned out to be crucial for things like efficient gas storage and separation, letting one gas in while keeping another out. His work, published in the Anjawante Chemie around 2000, showed the first MOF that could reversibly soak up and release gas at room temperature and normal pressure. That was huge for practical applications.
Okay, so Robson proved design. Kitagawa proved useful dynamic behavior. What was missing?
Stability. A big problem with many early MOFs, even the flexible ones, was that they were often made in a solvent like water or alcohol. When you tried to remove that solvent to activate the pores for use, the whole structure could just collapse.
Ah, like taking the scaffolding out too early?
Pretty much. And that's where our third laureate, Omar Yagi at Berkeley, made his defining contributions. He tackled stability head-on and really systematized the whole field.
Okay, how did he do that?
Well, first he actually coined the term metal organic framework, MOF, which stuck. But technically, his huge advance was popularizing and refining the concept of using those secondary building units, the SBUs, as the metal cornerstones.
Right, the SBUs, you mentioned those. How did they help with stability?
Before Yagi's systematic approach, people often used single metal ions as the connection points. These single points could be weak links. Yagi realized that if you used preformed, robust clusters of metal atoms as the SBUs.
Ah, stronger building blocks from the start.
Exactly. These robust clusters could hold the structure together much more effectively. The resulting framework was far more stable. Even when you removed the solvent and heated it up, it became permanently porous.
And this led to a breakthrough material.
It did. In 1999, his group published a landmark paper in Nature describing MOF5. This was really the poster child. It had incredibly high porosity and it was stable. It could survive temperatures up to 570 degrees Fahrenheit, that's 300 Celsius.
Wow.
So by establishing this SBU approach, Yagi essentially gave chemists that reliable Lego set they needed. It turned MOF creation from, a bit of an art into a much more predictable engineering discipline. Reticular chemistry became truly systematic.
Design, flexibility, stability, the trifecta. Okay, so now they have these amazing materials. Let's talk superpowers. How are MOFs actually being used to solve these big global problems you mentioned?
Right, the applications. This is where it gets really exciting. Let's start with climate change. CO2 capture.
We hear a lot about carbon capture. How are MOFs better than what we already have?
The key advantages are selectivity and energy efficiency. Current methods, like using liquid amines to scrub CO2, work, but they take a lot of energy, especially to release the CO2 again for storage or use.
Right, you have to heat them up a lot.
Exactly. MOFs, because you can tune the pore size and chemistry so precisely, can be designed to grab only CO2 molecules, even from a mix of gases like factory exhaust or even just the air around us. And crucially, they often release that CO2 with much less energy input. Maybe using just a small temperature swing or pressure change.
So potentially much cheaper and more efficient carbon capture and storage, CCS.
That's the goal, making CCS economically viable on a massive scale.
Okay, what about water? You mentioned getting water from desert air. That sounds almost miraculous.
It really does feel like it. This is work pioneered by Yagi's lab again, using a specific MOF called MOF 801. They've built devices that basically just sit out in the open.
Okay.
At night, even in incredibly dry environments, we're talking humidity down as low as 17 to 32%, really arid conditions.
Oh, that's dry.
The MOF passively absorbs water vapor molecules directly from the air, it just sucks the moisture in.
Using no energy, just sitting there.
Right. Then during the day, the sunlight heats the device, and that heat is enough to make the MOF release the water it collected, but now is pure liquid drinking water.
That is incredible. How much water are we talking?
The reported rates are pretty substantial, around 3.5 liters of pure water per kilogram of MOF per day. That's potentially enough to provide drinking water for people in remote, arid regions using only sunlight. It's a genuine breakthrough for water scarcity.
Definitely a game changer.
Mm.
Okay, climate, water. What about energy itself?
Big applications there, too. Think about clean energy fuels like hydrogen or methane, which is the main component of natural gas.
Right.
Storing these gases efficiently is a challenge.
Yeah, you need bulky, high-pressure tanks.
Right. But MOFs, with that massive internal surface area, can absorb far more gas molecules at lower pressures within the same volume. So you could have lighter, safer, higher capacity fuel tanks for hydrogen cars or natural gas vehicles.
Better storage. What else?
Catalysis. Many industrial chemical processes rely on catalysts to speed up reactions. MOFs can be designed to be incredibly efficient and selective catalysts. They can make reactions happen faster at lower temperatures, and crucially, produce only the desired product without wasteful or toxic byproducts. That means greener, more efficient chemical manufacturing.
Okay. And the last area was medicine. You mentioned microscopic Uber drivers.
Yes, that's a fun way to put it. Biocompatible MOFs can act as drug delivery vehicles.
So you load them up with medicine?
Exactly. You load the drug molecules into the MOF's pores. Because you can design the MOF to be stable in the body, but perhaps break down or release its contents only under specific conditions, like the slightly acidic environment around a tumor.
Ah, targeted delivery.
Precisely. The MOF carries the drug safely through the body, protecting it, and then releases it right where it's needed, like at a cancer site. This means you could potentially use lower doses, hit the target more effectively, and reduce side effects on healthy tissues. It's a big step towards truly precision medicine.
Wow. Okay, this deep dive has been fascinating. These materials, MOFs, they really do sound like engineered magic. So for everyone listening, let's boil this down. What are the absolute key takeaways from the 2025 Nobel Prize here?
I think there are three main things to hold on to. First, the big picture. MOFs are a victory for rational design. This whole field of reticular chemistry lets scientists literally build new materials, atom by atom, following a blueprint. It's a fundamental shift beyond just using what nature gives us.
Right. Design over discovery. Got it.
Second, the properties are just off the charts. That incredible internal surface area, the football field in a sugar cube, and that unique breathing flexibility. These characteristics give them capabilities that previous materials just didn't have.
Unprecedented capacity and dynamic behavior. Okay. And third?
And third, this isn't just lab bench chemistry anymore. It's leading to real, practical solutions for huge global problems. We're seeing applications in environmental protection, clean energy, clean water, and advanced medicine starting to emerge right now. This is technology with transformative potential.
Absolutely. I love how the Nobel Committee put it, saying Kitagawa, Robson, and Yagi gave chemists the tools to design materials from the atom up, like master builders drafting blueprints for invisible cities.
That's a beautiful summary. Invisible cities built atom by atom.
Yeah.
And, that idea of atomic level design, it's really just the beginning.
Oh, what's next?
Well, now researchers are heavily using computers, machine learning, AI, to design MOFs even faster. They can computationally screen thousands, even millions of potential structures to find the perfect MOF for a specific job. Maybe one nobody has even thought of synthesizing yet.
So using AI to accelerate the design of these molecular blueprints.
Exactly. Predicting properties before you even go into the lab.
Which brings us to a really interesting thought to leave everyone with. If scientists now have these tools, these principles of reticular chemistry and AI to help them design materials with atomic precision for almost any function, cleaning water, storing hydrogen, delivering drugs, what are the real limits now? For sustainable technology, for solving problems, are we entering an era where material limitations are essentially becoming a thing of the past, solvable purely by design?
That's the big question, isn't it? What problems can't we solve if we could build the perfect material for the job, atom by atom? Something to think about.